There are three mechanisms of heat transfer: conduction, convection, radiation. The choice of simulation tool to use depends on which of these three mechanisms are taking place. Conduction is the transfer of energy between solids that are in physical contact. Convection is the transfer of energy between a solid and its surrounding fluid. Radiation is the transfer of energy from a solid to ambient or between solids by electromagnetic waves. In most cases, heat transfer problems involve a combination of conduction, convection, and radiation. Looking at this electronic enclosure, if you are only analyzing conduction between components which are in contact with each other, then you are really looking at this board only. No enclosure, no fluid, no air around the components. In this case, FEA is faster than CFD. Here is the result of the FEA analysis with conduction only. You can see the temperature gradient across the board expressed in colors. If analyzing conduction and predictable convection, then FEA does an acceptable job. Let's first talk about what predictable convection means. It means forced convection, such as from a fan or a blower or anything that creates airflow when you know the convection coefficient, i.e. predictable. Many engineers would apply a constant convection coefficient to all the exposed surfaces of the component as a method to create predictable convection. You can use coefficients found in reference tables, such as the one shown here, or calculate one by hand. As we said, in this case, you can use FEA. If it is not predictable, or if you want better accuracy by not applying a constant coefficient to all components, then use CFD. Here is the typical scenario of when to use CFD. In this case, we are modeling not only the board, but also the enclosure, the convection source, and the fluid volume within the enclosure. In cases where convection is not predictable, such as forced convection, where you don't want to apply constant coefficient to component surfaces, CFD should be used, not FEA. Likewise, if buoyancy from natural convection is the primary convection mechanism, for example, your motor has no fan, this system is not predictable. CFD should also be used, not FEA. Here are the results of the CFD analysis. You can see not only the temperature gradient across the board, but also the dynamics of fluid flow within the enclosure. The streamline animation and cross-section of the enclosure will help you determine if there is recirculation or areas not getting exposed to forced convection. These CFD results will allow you to quickly see the consequences of different designs. Analyzing radiation is more important for some industry than it is for others. In the high-tech industry, radiation is often ignored because it is negligible compared to the impact from conduction and convection. You can model radiation with FEA or CFD. However, if you're going to model radiation with unpredictable convection, then remember, you should use CFD. You can use FEA if you have predictable convection and if you know the emissivity of the radiating components. However, radiation analysis with FEA can get involved. You may want to model radiation between surface to surface or surface to ambient. In the case of surface to surface, FEA is not practical because the calculation of view factors takes a long time and it is computationally intensive. In the case of surface to ambient, you can use FEA if you have or look up an emissivity value for the type of material you are using, or you can simply use CFD, which I would recommend. From a practical perspective, it is much easier to model radiation with CFD no matter which application. Here is a summary of when to use each of the heat transfer simulation tools. Note that CFD should be used in most of these scenarios. In addition to the standard CFD tool, You should know that SOLIDWORKS Flow Simulation has two industry-specific add-on modules, one for HVAC and the other for electronic cooling. HVAC, which stands for heating, ventilation, and air conditioning, has more advanced radiation models than our standard CFD tool. Electronic cooling is a dedicated simulation tool for thermal management. It has capabilities that automate the simulation of heat transfer, such as PCB generator, two resistor component, heat pipe, dual heating, and more. FEA and CFD are two great tools to analyze heat transfer, conduction, convection, and radiation. Generally speaking, CFD is more accurate because it captures the effects of fluid flow better than FEA. Despite its limitations, most engineers have historically used FEA to simulate heat transfer because it was the only tool they had and it was easier and cheaper. But now, SOLIDWORKS Flow Simulation integrates the power of CFD into the platform that you use every day. CFD is a better simulation tool for heat transfer and it is just as easy as FEA.